Shall we start? Good morning, everyone. Welcome to this third edition of the Deep Learning Barcelona Symposium. My name is Christian Canton. I'm coming from Meta AI, formerly known as Facebook. And this is a great day today because it's for me, it's my first conference in person after almost 2 years, which is it gives me chills just to think that I'm talking to an audience, and to all of you to welcome to this conference today. So I know that today this is the first real presential conference for many of you. So we spent like almost the last 2 years at home doing research, and many of you like submitting your papers and presenting them in virtual conferences, which is a very different kind of scenario than the one that we have here today. Conferences is not only about sharing your knowledge, sharing your papers, your research. It's also about meeting your colleagues, doing networking, finding new opportunities, discussing ideas in posters, in oral sessions, and that's something that we're going to be doing here today. Which again, it's very magical because for many of you, it might be the very first conference. I heard that many of our young researchers haven't had the opportunity to go to a conference. Many PhD students haven't been able to discuss their ideas with their colleagues in person for a while. So today, it's a very special day. So in this edition, as I mentioned, like our third edition in the Deep Learning Barcelona Symposium, we're going to be touching on a variety of topics. We're going to be like touching on the classic, on computer vision, on 3D, on speech, on NLP. But we saw a lot of submissions and a lot of like contributions that have bleed into other areas of research, such as life sciences, applications on new drug design, medical diagnosis, genomics, which is something very interesting. We see that AI has started to move beyond the classical topics into new places, which is very, very interesting. So why are we here today? Why is this workshop conference today very different than many others? So Deep Learning Barcelona Symposium joins us in a very specific thing. We have a relation with Barcelona. Many of you do research in the city. Many of you have studied here before, or many of you just like have this city in your heart. That's why we are here today. It's amazing to see all the research that you did and that we have the opportunity to see it here today. It's very important as a community of researchers related with Barcelona that we keep doing that. It's important that we gather, that we create new ties, that we meet each other, because that's the relationships that we build today are the ones that are going to be important for the future. So for today, we have 32 talks, which are going to be very interesting, and 41 posters that are also very, very interesting. We have a bunch of local entities and universities represented. We have like UPC, CVC, University of Barcelona, Pompeu Fabra, and many others. We have researchers that come from abroad. We have people from MIT, people from Stanford, Columbia, and also many other universities, which is pretty amazing. And a number of different corporations like Meta, Amazon, NVIDIA, Element AI, Global, and many others. So it's amazing to see the amount of talent and the amount of good contributions that are spread all through the world and all through this number of companies that come from Barcelona. We have 3 very relevant keynotes. We have John Bruna from NYU, we have Alexander Bow from Apple, and Joan Serra from Delby, which are going to give three keynotes through today and tomorrow. And I also wanted to highlight that this event has been possible thanks to an amazing committee of organizers, local and abroad. We have people representing the rich fabric of researchers and investigators that are related with Barcelona. I also wanted to mention that we have a number of different sponsors that has been made this possible. We have Meta AI, we have Global, we have CBC, WOC, UPC, ETZB, and a bunch of others, which are going to support this event today. It's important because that also gives you the importance or the perspective on how corporations and other places like to support this event. I wanted to mention that some of these companies, among them, as far as I understand, Meta AI and Global will be holding some recruiting events, just for awareness, like I think today is Meta and tomorrow is Global. I really encourage everyone to attend to learn what these companies are doing and what are the opportunities that might be there for you. And I also want to conclude, sorry, my papers here. Yeah, I want to also to highlight that something that is very important and something I learned over the years of doing research is that it's not only about the research that you do, it's not only about the papers that you publish and the talks that you give, it's about the relations that you can establish. And that's what makes a community vibrant, a community that is self-sustained, a community that generates opportunities for the new people coming and for the ones that are already here. So that's what I encourage everyone, not only to talk in the coffee breaks, to get to know each other, to like ask interesting questions during the sessions, but also to participate in our mentorship program. For the first time this year, we organize a mentorship program that is going to happen to the coffee breaks in the morning and the afternoon, where like you will be able to ask questions to more senior people, I mean for the young ones, or even for the senior people to talk among each other. I would like you to talk, if you are interested, to talk with our coordinators that are going to be here today. It's important that we mentor each other, that we help and we grow together. So that's something very important. Just to conclude this opening of the session, unfortunately, we are still in COVID times. This is very sad. This is true, but this is what's happening. I really like, I like to see people in person coming here, and this is important. We should be very respectful with our measures for COVID. Everyone wants to spend holidays with the loved ones, not like confined at home, so please be very, very careful. Take all the measures. You have like your hydrogel to clean your glasses. I do glasses, sorry, your hands. The mask, please wear it all the times and be very careful. Also, for those that are not here today, this event is going to be like online for those that are interested to follow up. So it's okay if you need to leave today. I mean, the data will be there for you to watch it later. So with that, I would love to, again, welcome everyone to this third edition of the Deep Learning Barcelona Symposium. I hope next year it's going to be more crowded. We're going to have our masks off. It's going to be different. It's great that this year we managed to have it in person. And please enjoy, learn, network, make it a success, okay? Thank you very much, everyone, and let's start with this amazing conference.
Hello, everyone. So welcome to the first session of the symposium that is going to be dedicated to the 3D domain. My name is Albert. I'm a research scientist at Meta. And today we'll have 5 amazing papers. So we'll have 1 presenter per each, 10 minutes each presentation, and then after each presentation, we'll have a round of questions. So if you have any question, comment, whatever, just like make sure to ask it. We are here for this. Okay, so without further ado, let me introduce you. Let me introduce you to Javier Romero. He's also a research scientist at Meta, and today he's going to be talking about his CVPR work on human reposing.
Thank you, Albert. Okay, yes, I'll be presenting SPICE. This paper, it's ICCV, by the way. There was a mistake when I was writing. Is it sounding in here? Yes, 1 second. Okay. I'll be presenting this mouthful of a title, which is Learning Realistic Human Reposing using Cyclic Self-Supervision with 3D Shape, Pose, and Appearance Consistency. I hope you're awake now after that. I'm Javier Romero. This work was done by Xixian Liao in his internship in Amazon, where most of the authors, including me at the time, were working before ICCV. And as Albert said, I joined Meta a few months ago, so that's my affiliation right now. So let's get started. So what is SPICE? if we have a source image like this, and we want to repose it to a target pose that here is represented as this set of points representing the skeleton, in order to obtain a new image that represents the same person with the same appearance, but in a new pose. This is the problem setting. And this has been done before in a number of occasions. There is two main branches of prior work. One of them is using supervised data. And here with supervised data, I mean paired data. There is at least 2 images, potentially more, of the same person wearing the same clothes with multiple poses, so that you can train the system to transform one image to look like the other one. However, that is restrictive in terms of the data that you can use. So there is another branch of prior work using unpaired data, where you only need one image. And within these approaches, there are also 2 branches. One is, for example, the paper from Albert from 2018, where by using 2D key points and instead of relying on the direct supervision of ground truth data, using the cyclic supervision to basically transform back the image that you transformed to the original one and comparing that, he obtained some results on this reposing problem. There's another smart line of work where they basically take the image, extract features that relate only to pose and only to appearance, disentangling it. The appearance is, for example, the appearance of parts, in a way that then you can inject new poses with the same appearance representation, or new appearance with the same pose representation, and you can repose in that way. Like all these prior work, treat the problem in 2D, and this will be a differentiating factor with respect to our problem, which I'll describe in a second. So, recapping SPICE, why is it different? First, it's self-supervised. It belongs to this second branch of work, and it's actually using this cyclic supervision to solve the problem. And importantly, it's exploiting 3D information about the body to obtain better results. Okay, let me revise a little bit what are the inputs to the algorithm so that it's a little bit clear how is this going to work. We have an image, an input image, source image, IS, from which we will grab this appearance and shape of the person. And we extract its pose. We can use, for example, open pose to do that. This would be PS. It's represented as a 2D skeleton. And we have a target pose, PT, also represented as a skeleton. This would be a typical setup for cyclic consistency, for example, if we want to inform the algorithm in terms of 2D pose estimation. We go a step farther and convert those poses, represented as skeletons, into a rendering which, even though it's still 2D, represents the shape of the person and includes information about occlusion between parts, the volume of the person, etc. So in order to do that, we're transforming that skeleton to a 3D body mesh with simplify as a method. You can use a number of methods nowadays. And we render that 3D body with a color wheel texture to transform it into that colorful render. We call that render RS in terms of the input. There will be also an RT for the target pose, but these are the inputs to our algorithm. Source image, render source, pose source, and the pose target. Now, we take all these inputs and we're passing it through a backbone to convert it into the target image. That backbone is very, very similar to the Ren et al. Previous work backbone, which I'll very, very briefly comment here the idea of how it works. This backbone has 2 parts. Basically, it contains a part that estimates optical flow between your source and your target. Remember that this is not a typical optical flow problem because you don't have the target image. You have to estimate flow between your source image and your target pose, your target skeleton. So it's a little bit different from the typical one. They have to use some tricks in order to do that. With that flow, they compare your source features and your target features so that you can use that information about how similar the source and the target is to place attention on whether you want to grab pixels or features from your target from your source image and copy them to the target, and where do you want to hallucinate new data. This is the basic scheme of Ren et al. Backbone, which we are using in our problem. So we have our images, we produce a render image. if we had paired data, like Ren et al., we could just compare this, and we would be done. However, in our case, we don't have paired data. So we have to do something else. As I said before, one of the options for solving this problem is to use the cycle consistency trick. So now we take that target image and we change the roles of the target and the source. We are using the render target, the post target, and the post source in a reversed way to transform it through the same backbone, Ren et al., to IS hat, which should be looking as similar as possible as the source image. And we're comparing those two images in terms of 3 typical losses. This is the perceptual loss, VGG, the style loss. This is computed on features on VGG, but passed through the gram matrix, so that you're not comparing feature to feature, but the correlations between features that is used in style transfer. And a pixel loss, which is just comparing the pixels. Again, one would think we're done, right? Like we now have a cycle, it will work well. However, the problem is that there are trivial solutions possible. You could just, there is nothing preventing from the source image to be copied to the target image and back, because there is no consistency between the source image and the poses that we want to achieve. So we have to include a few other losses. And here's where we also start using a little bit more the 3D. First, we want the target image that we want to reconstruct to be coherent with the pose that we have extracted from the target pose in 3D. So we're comparing the 3D pose as extracted from the simplified method between those two entities. So we want the pose to be similar. We want the shape of the person that we are depicting also to be similar. So again, we're comparing the beta parameters of the simple model that represents the body shape of the person between the image and the target that we have. And we have an appearance loss, and here I'll try to explain this shortly. If you have two images, if you want to repose the image just slightly, which is a relatively common problem in fashion, you just want a change of weight in the hips, etc. Intuitively, you could reuse this information to say that the torso should look very, very, very similar, right? So this is not always the case. Sometimes you have a large change in pose, and you cannot reuse those features that match. Here, you could, because the dress is symmetric, but the back could look completely different. So what we're doing here is to define two areas. This is defined very coarsely, but we could do it in a more fine-grained manner. We define two areas of the body, the front of torso and the back torso, and render them so that we have an idea of how similar the pose is in here and which pixels can be compared directly. We see here that the torsos occupy a similar amount of space in there. We can put a bounding box around these torsos and compare patches of those two entities, and add an appearance and a style loss in there. If your pose is slightly different, you still have also a red area in the lower frame. However, this is not as useful because there is a large change in perspective. For that, we are weighting this loss by the rotation of the hip. So it's perceptual and style loss on patches where the mask is common, but weighted by the rotation of the hip. Obviously, if there is no overlap between the masks, there is nothing compared, and this doesn't contribute to the loss. So this is the appearance loss. And there is, finally, why not, adding an adversarial loss to make it look just a little bit more realistic. We want the images to fool a discriminator, and this is conditioned with the render. And there is also a flow loss because the flow is computed. This is used for Ren et al. We want the flow to be good, so there is another loss on the flow. Okay, so that is the method. I'm going to show results now. First, overview of the results. You have 3 by 3 matrix in here. In each of these blocks, you have the source, the target, and our result. As you can see, we are collecting, we are representing the general shape of the person pretty well. The identity of the person is conveyed also reasonably. The garments, up to the extent in which this could be done deterministically, are also conveyed relatively well. If you look, for example, at the first column, bottom row, you see differences, obviously, because from the front it's very difficult to know how the back will look like, but it's a relatively good result. Don't get discouraged to not work on this problem, because in reality, when you zoom in, you see that there is still work to do. There is still zombie eyes to be fixed, hands that have 6 fingers, so there is still a lot to do. When you check these papers, always try to see images at a decent resolution so that you can see what the differences are in reality. But the results are relatively good, especially if we compare it with previous work. When we compare it with other unsupervised methods before, we see that the previous approaches had all sorts of artifacts. They were not that realistic sometimes in terms of the colors, the shapes. The garment was fusing with the skin. There were all sorts of artifacts. And our results, which are the third in each of the blocks, is the most similar to the original images. Also, this, by the way, is, and you can check the results in the paper, if you check the FID scores, our scores are substantially better than any other unsupervised previous method. And when we compared with supervised method, remember, supervised requires not only to have one image per person, but having multiple of them with the same garments so that you can use a supervised loss. It compares pretty well with most of them. The only method that is a little bit better than ours is RenderAll, the one from which we are using the backbone. If you look at the results, the others, for example, in the middle column, do not manage to represent the garment very well, very accurately. It's blurry. RenderAll has pretty good results. But again, remember, RenderAll and all the other methods in here are using paired data, which we are not using. We are using only one image per person in order to learn that. And just to finish up the analysis in here, an ablation study. So it's always useful to know, okay, we've added 3 losses for the cyclic consistency loss, 3 losses in terms of pose, shape, and appearance, and then we also have the float. We have lots of losses. Were all of them necessary? So here we are showing examples with and without those losses. This first row is showing what happens when you remove the pose loss from the algorithm. And I don't know if it's very visible in there. I think it is. What happens when you remove the loss, a typical error is that you get depth ambiguity. So here the legs are ordered in a weird way, for example, on the right. And on the left, the legs are also a little bit funny on the upper part. So when you force your result to be consistent in terms of pose, you prevent those errors. When you introduce shape, you get some weird shapes like the waist being too thin, or the butt being a little bit too big. Note that our loss here in shape is a little bit coarse. The beta models of the simple model are not super fine-grained. So there is still a lot to exploit in here if you introduce local losses of, that try to encourage the shape to be similar. This is just one approximation. It seems to help a little bit. And the appearance loss, remember, the one that is using these patches in order to compare the perceptual loss in patches of the image, helps representing well when the pose is relatively similar, representing well the original pattern and make it less blurry. And the final thing, just as a funny example, although it's not going to move very well in here, this wasn't trained on motion data, but if you just take a video, compute pose per frame independently, and map and use our method to repose the original source image, which is on the top, according to the motion that is extracted frame by frame to the one on the bottom left, you get results that are not too unreasonable. Obviously, you get a little bit of flickering results in areas that are not so clear from the source image. For example, sometimes the hair is not completely coherent, but for a method that has been trained on a purely frame-to-frame basis, it's not too bad. And with that, I conclude and I say thank you.
Thank you very much. So does anyone have questions? If you have any question, just raise your hand, and then Enric will bring you a microphone.
one small question. Why there are mostly women in your data set? Have you tried with men?
Very good question. It's positive. It's what is it called? Positive discrimination? No. It's a data set. So this data set was coming from the Amazon fashion data set, and it contained mostly women in there. I don't know if in the images it's always true, but it's true that, yeah, all the images that we have, at least in this presentation, were all women. I think it's biased from the data set.
Thank you for the presentation. I have just a small question. I think you show your network architecture is quite complex, has many trunks. Do you train this end-to-end, or you use some pre-trained weights? And if you use pre-trained weights, where do they come from? How those
Sorry, I didn't understand. If I train what?
You have many networks, right? And how do you initialize these networks when you train? Do you use random weights, or they come pre-trained from other methods?
That's a very good question. I honestly cannot remember for sure how this was done. I don't think it, so for example, the backbone, the renderal backbone, which is the biggest chunk in there, I don't think it could be retrained. I think it should be coming from scratch because there is a slight difference in the computation of the flow. Renderal, when it computes the flow, it has a loss that basically says when you rewarp the original image into the source image, it should look similar to the image because you don't have ground truth flow, right? In our case, we don't even have the target image, so we cannot have that loss. When we compute the flow, we use the renders. So given that that is different, the flow for the renders wouldn't have worked the same. I think it probably comes from scratch. So, but I'm not 100% sure, but positive about it.
Okay, thank you.
Sure, thank you.
Okay, let's thank the speaker again. Okay, so let me introduce you to the next speaker. He's Dan Casas. He's an assistant professor at the Juan Carlos University. And today he'll be talking about his CVPR on cloud dynamic simulation.
All right. Does it sound okay? Yeah. Okay, so my name is Dan Casas, and I'll be presenting this paper with a long title that we presented at CVPR. Originally, I hate long title papers, but in that case, we didn't really agree on the title, so we put everything there. But the good thing is that I can use the title to introduce the paper because it has everything, right? So just to, instead of reading the title, I'm going to go step by step over the title and introduce the work and motivate the work. So, so the title ends on, with a virtual try-on, and by virtual try-on we mean that we want to test and visualize how a certain digital garment would look on a virtual body. So here we have a body that changes body and shape. It's a bit weird because through the middle of the animation, the body changes the shape, so it gets bigger. And then by virtual try-on, what we mean is that we want to approximate how the garment would deform according to the body shape. That's what we do with virtual try-on, and we do it in 3D in this case. So the way we want to do this is we want to do it in a learning-based approach. Particularly, we want to use a generative method in a way that we learn a neural network that from some latent representation, it outputs valid configurations of the garments. This has certain advantages that I will introduce through the talk. The traditional alternative to this would be to use a physics-based simulation and then just simulate the garment on top of the body, but this is expensive. So we want to try to do it with neural networks. And probably the most relevant part of the title is the self-supervised collision handling. So here you see a comparison with our results and the previous works, and you will notice some collisions on the previous works. So what happens here is that methods based on data, sometimes they are not accurate enough to resolve collisions with the underlying body. So in our case, we are particularly interested in solving these collisions, right? So we want a method that it outputs valid configurations of the garments. All the previous methods, they output pretty good deformations of the garments, but these deformations penetrate the underlying body, and then they require some post-processing step. Okay, so basically this is what we try to solve, okay? Basically when we tackle this problem, we want to first try to understand what's going on here and why this happens, and then basically our contributions are different steps towards making this not happening. Okay, so now that we understand the title, I'm going to introduce like the naive pipeline for data-driven 3D virtual try-on. There's many works that attempt to do that in the past. By the past means like the last 5 years when this topic can come up. So the traditional approach is you have a physics-based simulation of garments, and you create a data set, and you try to learn a neural network that in a supervised manner learns to deform garments, right? So we have some physics-based simulation. This is slow, but we can do it overnight. And then basically the most naive way would be you have a template of the garment, and then you have some representation of the underlying body, and then you learn a network. This could be even an MLP that outputs, for example, 3D vertex offsets, or you could also do some fancy graph neural networks here. It doesn't matter. They all suffer the same. And then this neural network outputs some deformations of these garments. You will notice that here the garment is in a rest pose, and basically we do this to have a more canonical and normalized representation. So when we learn this, we learn offsets on T-pose, what we call T-pose or rest pose, right? So you can learn this in a supervised manner. Many works do that. And then at runtime, what you do is you predict your nice wrinkles, and then you repose these nice wrinkles, right? So what you see here on skinning plus post-processing, what we do is post-processing is collision fix, right? And skinning is basically reposing the garment. Okay, this looks really nice, but it has many problems. So this is a skinning step, which is basically re-articulating the underlying garment, basically borrows stuff from this guy here. So we know how the person deforms, articulated, and then we apply the same articulations to the garments. But the problem is that many times it is defined constant. Like this body is kind of rigid, so the articulating is fine, but garments deforms dynamically. So if you apply a constant skinning function, you end up with problems. To solve these problems, all these methods use this post-processing, that even if you implement in the GPU with the fanciest way, it's actually the bottleneck of the system, right? So the bottleneck of the system is actually fixing the problems. So this is previous work, and basically in our method, what we try to do is solving the requirements or the limitations of the previous work. So we do this with 3 fundamental steps. So in the first step is to find a new representation of the garments. So instead of using this T-pose or rest pose representation of the garments, we want to also remove the shape of the human, right? So this way we can have garments represented in a unique shape. So you have to, it's a representation that it doesn't matter what is your shape, the wrinkles of what you're wearing are going to be projected into the same space. So this further normalizes the problem. So basically, if we have these nice physics simulations, we want to project them into a canonical space that it removed both pose and shape attributes. Okay, so you need to pay attention here. For example, this guy is a little bit bigger than the others, but in the normalized representation, they use the same shape. Okay, it's exactly the same 3D mesh underlying. Right? So we want to remove shape and pose attributes from the garments. And then the idea is that if we do the learning there, this is going to be much easier, right? Because it's a more normalized space, right? We always want to normalize data and project to a space that is easy to learn, right? So in that space, we can learn the wrinkles, but everything related to the body, we get rid of it, okay? That's what we want to do. So in a way, we want to remove shape and pose body deformations from the garments. So we want to do that, and then we want to train our networks on the representation on the right. And then at runtime, we want to add, again, the body pose representations. That's what we want to do, right? So basically what we're doing is we are borrowing all the stuff we can borrow from the human body, which is how we deform, and disentangle this from how the garments deform. The good thing is that in the literature, there's a lot of knowledge on how humans deform, not that much on how garments deform. So now the question is, how can we do that? And so if we think about the problem we're trying to solve here, so imagine a vertex in this t-shirt. So this vertex, which is not attached to the surface of the body, should go somewhere rare, right? So we want to kind of find a function that projects garment vertices into this canonical space, okay? The problem here is that this garment deforms dynamically, so the vertex is not always in the same position, right? So it kind of drifts over the surface of the body, etc. So this could be problematic. Well, it's in fact problematic, right? So the way we do that is with our second contribution, which is this diffuse body model. Here you have this sentence, because it's funny. This other paper came up with the same idea, and they have a better visualization, so I'm just using their visualization here. But it was concurrent work and for another purposes. So basically, the idea here is that we have a body model, that we know some function on this body model. This function could be how the body articulates, or some scheming parameters, or how the shape deforms. And basically what we want to do is we want to diffuse this function, only define it at the surface of the body to any point in the 3D space, right? So we want to diffuse some parameterization that only exists at the surface to any point in the 3D space. And then at runtime, we can query the function that we learn on the right for any vertex that has moved. And then from this query, we will get properties that we will be using, right? This is very similar to this trend that is nowadays about implicit functions to represent shapes. So basically, there's many papers that now try to learn, for example, distance fields with respect to surface. Here, instead of learning distance fields, we learned properties with respect to surface, which is not distance, it could be anything else. Okay, so that's the idea about this diffuse body model. So basically what we learn is we learn a function on the right for many properties of the body, for skidding weights, for pose blend shapes, shape blend shapes, which define how we get fatter and thinner and taller and short. So we learn all of those. And then when we use this to unpose the simulated garments, it looks much better, right? So here we have this nice physics simulation of a garment. And then when we project this physical simulation to a canonical space, which is what will hopefully make our learning easier, we end up with three different configurations, right? It depends on how you query the rigging parameters of these pixels, of these vertices. So in our case, because we learned this diffuse body model, we can much better unproject the garments into a canonical space. So then we get rid of all these collisions that happen here. If we would be using this method to learn our digital garments, then we would be learning with a data that already contains collisions, right? So we got rid of collisions in the training data, which is good. This works also for highly dynamic garments. So for example, here you should see that the skirt on the right, it doesn't suffer from these ugly deformations. So in general, we're quite happy because now we got rid of some of the problems we had. So we have a much better way to do skinning because we do this skinning with a diffuse model. And we actually have a much better data set because our data set does not have collisions, right? There's still one problem that we have, which is that if this neural network doesn't work too well, the output is going to be so bad. So imagine that this neural network outputs a really bad configuration of the garment. So this bad configuration would still collide with a human. So our third and I think most important contribution is to basically learn a subspace of correct configurations of the garments. And the traditional way to do that is basically with a subspace that you learn with a decoder. So basically the neural network would output a decoder, a latent representation of the garment, and then we would project this representation of the garment into the full space of the human. Now there's a trick on how we learn that. So the traditional encoder, autoencoder formulation is we have our unposed nice garments, and then we find a latent representation from which we can project back to the original representation. In here, you have to notice that this is supervised, so we need a lot of deformations, a lot of physical simulations. But the cool trick here is that we can learn this in a generative manner. We can use a VAE, a variational autoencoder, and we can learn this latent representation that follows a known distribution, right? This is a trick that is used a lot, right? So basically, if you do it this way, you can basically input stuff into the encoder, which you have ground truth, but you can also sample random values from a Gaussian distribution and still would output a nice representation. Now the trick, and I think this is the really nice part of the paper, is that for the output of the decoder, we can check the collisions with the human body, right? And then we can check if we are happy or not with these collisions. And then we can formulate a loss that prevents the decoder to output configurations that collide with the body. Now the cool thing is that if instead of the human mesh, we use our diffuse model, this basically becomes fully differentiable. What means is that I can, once I've trained the autoencoder, I can then basically sample my latent space many times and supervise the loss with the collisions. And basically this, what effectively does is that by exhaustive sampling, we're learning a subspace that do not collide with the underlying body. Okay, so we have an autoencoder that is fully differentiable and is self-supervised. And by fully differentiable, I mean that the collision check in the end is just running a network and see the result of the network. There is no physical check whether they collide or not, right? So this autoencoder is fully differentiable and self-supervised. Yeah, the pipeline is a bit tedious, so I didn't use this figure because there's a lot going on here. But basically, we first simulate data, project this data to a new canonical space, learn a subspace that do not suffer from collision, and then in the end, learn a regressor directly on this latent space. And basically, this allows us to push the state-of-the-art of digital garments quite a bit. So our work is the first that is able to predict these dynamic deformations of garment that do not collide with the underlying body. So these are the direct output of the network. So basically, it's a lot faster than any previous attempts. Basically, it's a lot faster because you need to do the post-process, which was the tricky part. And basically, it runs an interactive rates. So here we have this demo, which you can then change body and shape of the human, and the garment never collides with the underlying body. You can change the shape of the human, and then you see wrinkles appearing, etc. And the nice thing is that the representation that we learned is kind of aware of the underlying body. So this basically solves many problems that we had before. Of course, you can argue that the wrinkles are not too realistic, or they are still a bit stiff. There's a lot going on here. You can try to add more dynamics if you use a better recurrent network, etc. But it's pretty cool that the network is kind of aware of the underlying body. All right, that's it. That's a great work by Igor Santesteban, which is the first author of the paper in collaboration with Niels Touré from the Technical University of Munich and Miguel Otedui. And you can check, we have the models available on GitHub to check out, and also the data set is available. Thank you.
Okay. So thank you very much. We have time for one question. So please, if anyone has a question, just raise your hand.
Thanks for the presentation. This is great. The collisions problem is so tricky. So I wonder, when you inspect the results, have you found the holy grail of solving the collisions? Are you still having some of them, or are you actually having cloths that are in close contact with the body without collision? I'm basically wondering, beyond what we see,
yeah,
how good it is. It's like, what should we expect, that it's just perfect, or is it on one side of just leaving some space, or on the other of having some collisions but much better than what we've seen before?
Yeah, I mean, honestly, we had a little just collisions left. Just a little bit, like maybe one every 10 frames or something. Of course, the data was very well curated already. So there's two tricks here, right? So the first is to project the ground truth data into a nicer representation. And the second one is, once you have this nice representation, it makes your life easier. So it's a trick of both. I would say that the biggest drawback is this trade-off, right? Learning these VIEs is always a trade-off between realism and a nice distribution. And basically, I think we do lack a little bit of detail. Like if you compare this with a naive, fully connected layer, those would have probably higher wrinkles and higher dynamics. So it's still a little bit of a trade-off. But it worked pretty well. Like the self-supervision in that sense, it worked pretty well, I would say.
It's an interesting solution. Thanks.
Okay, thank you. So let's thank the speaker again. So next speaker is Enric Corona. He's a PhD student here at UPC with SIC at the IRI Institute. And today he's going to be talking about his work on cloth parametrization.
Okay, thank you for the introduction. Could you switch the slides to the Google Meet? Yeah, that's it. Okay, so I'm going to present our CVPR paper, SMPLicit, which was done with Albert, Guillem, Gerard, and Francesc. And so this work is framed in this topic of 3D reconstruction and 3D modeling of clothed human bodies. And the long-term vision that we have in this topic is that at some point we should be able to take some random picture of ourselves and to get a really good 3D reconstruction of body and hopefully the clothes. And with that, we might think of changing our clothes to someone else's, given their photo, or for some predefined clothes like these ones, and see how they fit into our body and how we look like, maybe animate our pose and so on. But when we started, we found out that previous works just assumed a fixed set of closed topologies, and they had to train a single model for each of them independently. So our goal is to remove this and try to fix this limitation by just training a single model that can represent all this diversity in the geometry that we have in clothing. So in particular, we would also like to start taking images as input and be able to get these reconstructions of these clothes for the geometry, but also we would like to move on from traditional approaches and get this semantic information of the reconstructions by getting a different mesh for the body and also for each of the different clothes. If we can do that, we should be able to do outfit editing almost in a straightforward manner by changing maybe some outfits, like here where we'll remove the jacket or the long pants, and we can add some boots or some hoodie like here. And we also should have control over the pose of the body, so we can change it or animate this person. But going back to the initial goal of being able to interpret or to interpolate different closed topologies, it was important to get a good 3D representation for this. So both, all of these boxes, point clouds, and meshes have been quite widely explored in the past, but they all have their limitations as well. So they are quite hard to integrate within deep learning models, and also they are discrete representations. So they are not great for interpolating topologies. So we're going to use implicit functions, which was a relatively recent representation for 3D objects. And the idea is that we can have an MLP to take some input point to predict whether this point is inside or outside the mesh, and also maybe predict the signed distance from that point to the boundary. So this would be a continuous representation, because we can take any point in the continuous domain and predict whether this point is inside or outside in a continuous manner. So they look good for representing different topologies. In particular, we're going to predict and sign distance fields using these MLPs, which will take as input some point, but also we want to parameterize this with some latent representation, Z, that will tell us how this cloth will look like in the 3D. So in particular, we also want this as be as low dimension as possible, and for that we divided these ZCAT and Z-style spaces, where for ZCAT we train another ConvNet at the same time that maps to this space by taking input occlusion maps. So these occlusion maps have this information of what parts of the body are occupied. So we can tell whether there's a hoodie or short or long sleeves in the cloth. And therefore, the ZCAD will also have that information. For this style, we expect it to represent more complex characteristics, like the tightness of the cloth. And then, during inference, we hope or assume that we can just move some of the slides semantically to tune the parameters of the cloth that we really want to represent at the end. So we could choose whether we want short or long sleeves in our clothing, or how long do we want this skirt or pants to be, and we will map them to these cloth parameters. This will be given as input to the MLP, and we can densely sample the 3D space to get the reconstruction using marching cubes. All of this can be also posed to some target pose using a similar approach as Dan explained before. And once we train this model, should be a video, so, okay. So once we train this model, which is a generative model, you can see on the left that we can sample different cloth representations and we can smoothly interpolate between them. So basically here we want to prove that we solve this limitation of previous methods and can interpolate between very different topologies, like hoodies, tops, or open jackets. And in the right, we can see the interpolation of a fixed t-shirt representation generalizing to different body shapes, some of which are quite different from the training data. But apart from having this generative model, we also wanted to use it for reconstruction. So we will try this with, by taking input 3D scans or input image and try to find the best cloth representation, G, that fits these, the clothes that we have as input. For instance, we can register the clothes from 3D scans by taking these scans as input on the left column and predict whether or register the most appropriate garments. In these experiments, we basically want to highlight the limitation of previous works. And for instance, our TaylorNet, which is our main baseline, and here we want to just mention that they assume either short or long sleeve t-shirts, and so they are not able to represent these sleeveless t-shirts or hoodies. But SMPLicit can generalize to this only by minimizing the chamfer distance between reconstruction and the input scan. Then we moved on to this task of reconstruction of cloth bodies from single images. And we make no assumption on the body pose that we take as input or the background. And we build this pipeline to get the 3D reconstruction, where we start with using state-of-the-art cloth segmentation and SMPL estimation to get an approximate pose of the body pose and shape, and also the cloth segmentation, which is telling us what kind of clothes is this person wearing. So we can almost directly reconstruct the clothes from SMPLicit by fitting the equivalent clothes and minimizing iteratively the difference between this segmentation and the projection of the reconstruction. This process also is giving us this semantic information in the 3D mesh that we're going to use later. So these are some results on this topic, where we run the previous pipeline for every image, for every person that we detect in these images in the wild. And we currently can reconstruct her upper body clothes, lower body clothes, and shoes. And the approach is quite robust with very challenging poses like these ones, and when tackling multiple people. But one of the important points is that we obtain one reconstruction for the body and then a different reconstruction for each of the clothes. So that allows almost in a straightforward manner to do outfit editing. This is an example where we remove the upper body clothes for the reconstructions and we make them dress with a hoodie, everyone. And this is the same example where we just change the lower body clothes for skirts. But okay, so the previous method was quite robust, but one thing that we are currently missing yet And we would like to have is a bit more high-frequency detail. We would like to have these more realistic reconstructions. So we added another step to this in this process, where we, by taking this input image, we use some standard hourglass architecture to predict front and back normal maps, and just modify the initial reconstruction to fit those normal maps. If we can do that, we're basically trying to leverage the previous approach, which was quite robust, because we were using fitting a parametric model for the body and a generative model for the clothing. So they will always give some reasonable results. But now we're trying to enhance it with detail, with these high-frequency wrinkles, which make this more realistic and more similar to the input image. To summarize, we presented this SMPLicit, the first method to represent very different topologies of clothing in one single model. And this was especially due to the 3D representation that we used for the clothes, and also to the fact that we use a very low dimension representation in the latent space. We also proposed this 3D reconstruction approach, where we can tackle either 3D scans or single view images, and we can obtain these reconstructions, layered reconstructions of the body and clothes, which we think can have potential for try-on. Thank you.
Thank you very much. So we have time for one question. Yes, yes, the mic. Yeah, so Dan.
Yeah, I guess I have to ask this question, like, how do you deal with collisions?
Yeah, in a data-driven way. So we learn basically also with a data set that doesn't have collisions.
So when you repose the human,
That's right.
You are a bit careful there.
We use one of your baselines, actually. So we're taking the closest point to get the skinning weight for each cloth. So we sometimes have artifacts when reposing, especially with skirts, which are the most complex one.
Okay, yeah, great work.
Okay, so let's thank again the speaker. So our next speaker is Eduard Ramon. He is a PhD student, also here at the UPC, and also in Crisalix. Now we are going to switch topics. So now we'll no longer talk about clothes, and instead we'll be talking about heads.
Okay, so thanks for the introduction, Albert. So yeah, I'm going to present H3DNet, also pronounced as HeadNet, which is a method for reconstructing human heads with high fidelity. And this work has been done at the company Crisalix in collaboration with UPC and IRI. So given a set of multi-view images of the head of a person, our goal is to recover the 3D geometry of the head, including hair and shoulders, and as much details as possible. And we focus on the few shot scenario. We consider down to 3 input images. So typical approaches for reconstructing 3D faces from few shot images combine convolutional neural networks with 3D morphological models. And this leads to geometries that looks like this, that represent usually the frontal part of the face. And while they are very robust, they are not very accurate. And also the topology is fixed, so you cannot represent other areas than previously defined. And recently, we've seen these implicit surface representations that has been proposed that are much more flexible and allow to represent geometries that are much more complex. And this, in combination with differentiable rendering techniques, allow to overfit the geometry to a singular scene. So we are spending the whole capacity of the neural network into representing a geometry. So we can achieve much more accurate 3D reconstructions. However, these methods are not very good in the few shot setup. So our goal here is to use these methods to work with very few images. So we want to use implicit methods in combination with differentiable rendering, optimize them for a given scene, but that we only have three images as input information. So our first contribution is related with the implicit surface representation. Instead of using a parameterized surface representation, what we use is a distribution of implicit functions. So this is the key point. And in concrete, this is a distribution of sign distance functions that we implement using the DeepSDF method. We take thousands of scans, of raw scans data. It doesn't need to be watertight meshes. As you can see, there are a lot of holes. We register a template, and we use this template to align all the geometries. And we normalize all these geometries to fit inside the unit sphere. And then we learn the DeepSDF model, and what we learn is the distribution of sign distance functions, where each sign distance function defines a surface implicitly. So when we have this model, what we can do is to sample from the latent space and generate arbitrary sign distance functions that each of them represents a surface. And the problem now boils down to estimating the Z vector that best approximates the images from the scene. To do so, we use differentiable rendering technique. In Propose, we use a modified version of the implicit differentiable renderer proposed by Jarif et al. And with this, we can already do few-shot-free reconstruction using implicit functions. However, we saw that the optimization process is very important, and that's why we propose a two-step optimization process, because depending on the scheme you use to optimize the scene, you can lead to much better, you can get much better results. So in the first part of this process, we just optimize the latent vector and implicit differentiable renderer parameters, which approximate the light field in the surface, but we keep the decoder weights of the DeepSDF model frozen. That is equivalent to just keep the distribution as we learned it before. We don't want to modify this distribution because the implicit differentiable renderer still knows nothing about the scene, and it can modify the learning process in a bad way. And once this process has converged, we unfreeze all the parameters of the DeepSDF model and the implicit differentiable renderer and fine-tune everything to get all the details from the scene. Since reconstructing heads is something relatively new because most of the methods focused on the face area, we created a data set called heads, which is made up of 23 scenes, and we are making it grow. And as you can see here, we have high-resolution scans of the whole head, which include hair and the shoulders. We also provide annotated mask, multi-view images, and ground truth camera poses. And with that, we evaluate our method. We compare first against 3D morphological models. As you can see, numerically, the results look pretty similar, but if we take a look at the heat maps, we can see that HeadNet is able to approximate much better some complex anatomical details like the nose, the chin, and the cheeks, which is usually 3D morphological models struggle at these areas. Here we have another comparison. You can see that HeadNet produces results that resemble much more to the ground truth qualitatively. Then if we compare against IDR, which is our baseline, we can see that numerically the results in the few shot setup are much better in our case, which is normal because IDR is not designed to work with few images. And as long as we include input images, both methods used to converge numerically to the same results. However, if we look at the heat maps again, we can see that with HeadNet we obtain surfaces that are much smooth and much nicer to visualize. Here is another example of IDR against HeadNet. We can see that the results of HeadNet are much more stable across all the input number of views. And while at 32 views, the results numerically can look similar, the surface is much well-defined in the HeadNet. So actually, using a distribution, a Peirce-Leland distribution, is helping a lot the learning process. This is a result in the wild. These are 3 images taken on the street without controlling any light conditions or anything. And you can see that the results resemble a lot to the guy in the image. And finally, here I would like to show you which impression causes a 3D reconstruction with texturing and so on when you use a 3D morphable model, which only is representing the frontal part of the face, and what happens when you use HeadNet or any other method that is reconstructing the full head with shoulders and so on. So thinking into real applications, if you want to talk to an avatar or whatever, you will feel much more natural talking with the result on the right, I think. So just to conclude, most of 3D morphal model-based approaches, well, they are very robust. They lack of precision sometimes, and they are constrained by the previously defined topology, so they cannot represent other areas. So we would like to solve that for some applications. And implicit representations work really well for that. However, we need many images. So if we have a user that wants to use this method, we cannot ask him to take 100 images of himself. We would like to ask 3 images, something like that. So we approach this problem and we try to insert previously learned knowledge as a distribution of sign distance functions, and in this way be able to use these kind of methods with only 3 input images. The optimization process plays a big role, so make sure to carefully tune your schemes. We propose a 2-step scheme that works pretty well in all our experiments. And just finally, some further work is needed. First of all, to speed up these methods, the orders of magnitude is still 3-4 times in comparison with 3D morphal models. So it is not viable for real-time applications. So there's a lot of work on that. And also to reduce the number of input images required, probably to 1 input image only. So that's it. Thank you.
Okay, thank you very much. So we have time for questions. So yeah, if anyone has a question. Okay, okay.
Yeah, it's great work. So do you also encode expression, or you keep expression constant? I didn't get that. Sorry.
Yeah, here in this case, we keep the expression constant because we focus a lot on the precision of the method. You can animate later on all these using some plane shapes or whatever. So,
I guess if the subject is not in a neutral expression, then your combination of implicit functions would need to learn different expressions, right?
Exactly. This is not. It couldn't work like this. So if you have an input image with some expressions, what you would like to do is to learn a distribution that considers these expressions, and that it should work as well.
Do you think this implicit representation will scale up to many expressions, or you would need additional, representations? Because, I mean, implicit representations are okay, but then there's at some point they saturate, no? So you need to.
Yeah. There are some works in this direction. For instance, using the formable nerve and so on. And in the space of implicit SDF, sign distance functions, there is a work, it's called I3DMM, in which they define a reference space, and they define the deformations on top of that. But we haven't tried, actually, so I cannot tell you if it will decrease the performance or not.
Okay, good work.
Thanks. Any other question?
Okay, so let's thank the speaker again. So our final speaker for this session is Guillem Brasó. He is also a PhD student at TUM, and today he's going to be talking about keypoint grouping.
Thank you, Albert. Okay, so a quick disclaimer, but this presentation is not going to be about 3D things. We're still with humans, but it's about 2D keypoint estimation. So yeah, I'm going to present this work from ICCV this year. It's called the Center of Attention, Center-Keypoint Attention for Multi-Person Post-Estimation. And this is joint work with Nikita Kister and my advisor, Laura Leal-Taché, at the Technical University of Munich. So in this work, we focus, as I said, on multi-person pose estimation. So this means that given an input RGB image, our aim is to localize the anatomical key points, so the skeletons of all persons in the image. And this is an old problem with a long research history, but still it remains challenging, especially in crowded scenarios where several humans overlap. So let's review some background on previous methods. So one of the dominant paradigms is top-down approaches. And this set of methods split the problem into two parts. The first one is object detection. So you apply an object detector to your image to obtain bounding boxes for all objects being present. And then basically for every object, you crop the image around the object and apply a CNN to perform single-person pose estimation, so to estimate the key points of each individual person. And this approach works well in simple scenarios. Oops. This should be green. But this naturally struggles when there's more than one person in the image, because the task is naturally ambiguous. So given an image with more than one person, it's not obvious which key point should be estimated. Another line of work that tries to circumvent this lack of robustness under occlusion is that of bottom-up methods. So what they do is that instead of detecting first persons, they instead detect key points without initially assigning an identity to them. So first you do identity-free key point detection. And then the second step is to take those key points and compute some form of pairwise similarities among them. So you try to essentially determine which key points are likely to belong to the same pose. Once you have this set of pairwise similarities, you do the grouping step. And essentially you usually apply some form of graph optimization algorithm that essentially clusters these key points in order to form poses. So this set of methods is generally robust under occlusion, but it's also often slow, so it has to rely on graph optimization methods. And for the same reason, it also yields methods that are in general not end-to-end trainable. Lastly, another line of work in the similar line is that of one-shot methods. And what they do is that they, instead of detecting key points, they first detect, let's say, a single key point corresponding to the entire person, corresponding to its center. And they simultaneously predict some heat maps that predict offsets from centers to key point locations. So essentially, this allows them to very directly predict poses by just combining center locations with offsets to their key points. And this basically yields a method that is quite fast, that's end-to-end trainable. Unfortunately, these offsets are often not very accurate, so they basically yield the trade-off between runtime and accuracy. In our approach, we basically try to get the best of both worlds, so we try to get the efficiency of one-shot methods with the accuracy and robustness under occlusion of bottom-up methods. So our main idea is to still rely on on person centers, but instead of using offsets, we also predict key points. And we pose the grouping task as essentially assigning key points to each center. By doing so, instead of relying on optimization, we formulate the problem as an attention task in between centers and key points. And therefore, we don't have to do any optimization, but we can formulate the whole thing in a trainable way, as we will see. So overall, our method is fast, since it avoids optimization-based grouping. It's accurate, since it relies on key points and not offsets. It's end-to-end trainable, and robust under occlusion. Okay, so let's have an overview of the methods pipeline. So given an input RGB image, we first apply an off-the-shelf, state-of-the-art keypoint detector that basically yields a set of heat maps corresponding to all keypoints in the image. And additionally, we add this extra heat map that corresponds to centers of persons. And once we've done that, we we basically extract the peaks from these heat maps to get a set of key points and get some features. So we get a feature descriptor for every key point that we extract from our CNN backbone and combine it with some positional information to encode this location and then feed all of these vectors corresponding to key points and centers to a transformer encoder that essentially just enriches features with contextual information. Once we've done that, now we perform grouping in between those centers and key points. And to do so, we perform attention in between key points and centers to essentially let key points, let centers, decide via attention which are their corresponding key points. So then we just directly use those attention weights to basically combine key points and centers. I will now explain a little bit more these two later steps of the pipeline. So for feature encoding, our goal now is to obtain some features for key points and centers that will allow us to do grouping among them. So basically, we have our set of key point and center detections that we have already obtained. And we have our CNN feature map from our detector. And basically, we extract the vector corresponding to each key point or center at their corresponding location. So we take that feature vector, and we feed it through an MLP, and then combine it with some positional encoding to obtain a vector representing it. We repeat this process for every key point in the image, as well as every center, until we have embeddings for all of them. We then feed all of this to a transformer encoder, and as I said before, what this does is that it allows different key points and centers to interact and, let's say, communicate with each other to obtain richer contextual features. Once we have all of these features, our task is now to group them. So to do that, we essentially compute cross-attention. So this means that we compute attention in between each pair of centers and key point embeddings. And attention here just means that we perform a dot product, let's say similarity score, in between each pair of them. Once we have these similarities computations, now we use a softmax to normalize them so that essentially each center focuses on a single key point of a given type. So let's say now we are looking at centers and we're trying to predict the left ankle of every person. What we're doing is essentially computing the similarity between each center and all the key points in the image, and try to make each center choose the most likely candidate to be its left ankle. In order to predict a pose based on that, we use directly the attention coefficient scores for every center. So essentially, we multiply these attention scores times the known 2D coordinates of the key point in order to obtain this weighted sum. And intuitively, if you think about, for instance, this orange center, in case its attention would be 1 for a single best candidate and 0 for all the rest, because as I said, we are normalizing this with the softmax, this would just correspond to outputting one key point's coordinates. So this formulation allows us to directly compare the predicted scores with the ground truth known locations for every person in the image. And essentially, we repeat this process in as many heads, so as many parallel heads as number of key points we are trying to predict for every person. So one limitation of this approach is that it will predict, it will try to basically match one key point for every center, regardless of whether, let's say, a person doesn't have a visible joint or not. So in order to compensate for that, we also predict some classification scores for every center that tells us which key points are visible for the person and which are not, in order to ignore the predictions for those that are not visible. In addition, we also predict an additional loss term to predict which centers are good candidates for centers or not. Also another note, so at test time we don't rely on this weighted sum, but simply replace it with an argmax to, instead of using this weighted sum, to just choose the best candidate. So let's look at some quantitative results. So we evaluate our method on CrowdPose, which is the main data set available for human pose estimation under crowded scenarios with occlusions. And our method obtains a significant improvement over state of the art, over 2 average precision points, while being over twice as fast as the best method. On COCO, which is the largest data set available for key point estimation, but does not contain many occlusions, our method still consistently improves upon state-of-the-art bottom-up methods with around 1 average precision point, and again, the speed improvement. So qualitatively, if we look at some results, we compare our method to higher HRNet, which is the state-of-the-art bottom-up method, with CenterNet, which is the state-of-the-art for one-shot methods. And we observed that our method usually performs best, does well under occlusion, and usually performs comparably to higher HRNet, despite being, as I said, more than twice as fast. We see more examples here where under clutter our method is robust and still can recover poses that other methods can miss. Lastly, here we visualize how our method outputs very, let's say, focused attention coefficients. So we visualize the input image, all the possible connections from centers to other key points. And lastly, how basically here we color code the attention coefficients from centers to key points, and we see that typically you see a single line for every type of joint, which means that our method just learns to focus on a single key point per person and type. Yeah, more additional results of this, where we see the same pattern. Okay, so in conclusion, we propose a novel attention-based framework for key point grouping that compared to other bottom-up methods, it's end-to-end trainable, and it's also more efficient. And more importantly, it's generally quite robust under occlusion. So thank you for your attention.
So thank you very much. Does anyone have questions?
Hello. First of all, thank you for the nice talk. It's a really nice work. I would like to ask, I've seen you have many results on images. Have you tried this on video, and how consistent do the joints prediction stays on video? Thank you.
Yeah, thank you for your question. No, unfortunately not. I have not tried this on video, but I'm just getting started with a project working on that, but I cannot really tell you more at this stage. Yeah, any other questions?
Then let's thank the speaker again. So this is the end of the first session, and then now Xavi is going to talk about what's next. Let's have a round of applause for all the speakers. One more. Thank you.
Hi, and thanks to all the presenters and actually all of you for being here. So I'm the local chair. I'm kind of helping organizing the logistics. I have some tips for you to enjoy the coffee break. So now we have a coffee break. It's outdoors at the garden. When you leave, that's the door you'll find on the right. There's also the posters there. We encourage you to visit the posters. Always try to avoid crowds because of the health reasons. And in addition, also when you exit the room, you'll see that on your left, there are 2 tables with t-shirts for you. Okay, so on your badge, you have this icon with a t-shirt, so you can go there with your badge, and they're gonna cross out your t-shirt, and you can get 2 t-shirts, one blue one, another orange one, okay? And I think that's all. Oh, also, when you get the t-shirts, again, avoid crowds. They will be there the whole day, so don't worry. I suggest that you go to a coffee break, and then when you see that there's nobody there, you go and get your shirts. There's plenty of time for that, and there are plenty of t-shirts. We will not run out of t-shirts, okay? Then finally, as one of the innovations from this edition are the mentorship and mentees sessions that have been organized by Miriam Bellvé and Agata Lepedriza. And now Miriam will instruct you, for those of you who have signed up, how to proceed.
Thanks, Xavi. So those of you who are participating in the first session of this mentorship that we are doing today, please let's meet close to the entrance of the poster area, okay? So we still need to define exactly where we are gonna be, but we are gonna be in the garden for sure, so let's meet close to the entrance, and then we will distribute the different pairs of mentees. So thank you.
One more last thing, for these speakers, for the next session, be here at 11, so you do the technical test, okay? Great, thanks a lot. Núria.
Bueno, perquè tot no la sala.
Hola.
Hola, Núria.
Xavi, ara et sento.
Val, anem a fer les proves, val?
Sí.
No sé, comparteix pantalla i fes veure com si presentessis. I jo estic aquí al costat, tinc els tècnics. I tu fes... Tu xerra i...
Vale,
tu comença com si anessis presentant, Núria.
Vale, també estic sentint música, per cert.
Sí, però és normal.
És correcte, sí.
Perfecte.
Bueno, espero que estiguis bé, Núria, per cert.
Sí, estic bé. Ja estic quasi curada.
Vale. Hi haurà altra gent que entra a la xerrada?
M'han dit que no sé.
Espera, una altra noia, serà la silencio, qui pugui. Vale, s'ha silenciat ella. I una noia que està a baix provant amb el seu ordinador.
Vale.
Vale, perfecte. Però podeu veure la meva pantalla, entenc?
Sí.
I em sentiu bé?
Jo sí.
Perfecte.
Vaig a la sala i t'ho dic.
Vale, espera, que crec que ara va una tècnica, ve xerrant, tu,
Vale, perfecte.
i jo crec que la tècnica... Bueno, però i ara a la sala no veu res, no?
Jo no veig la sala, no.
Ja, tu no, però la
vale.
tècnica ha anat a la sala, no sé què va haver, no sé què ha anat a mirar exactament. Bueno, tu queda't aquí de moment.
Sí.
Però jo ho veig bé. Què tal? Parla una mica, Núria.
Vale, molt bé, doncs... Això és el
Parla, Núria, endavant. Tira.
D'acord, doncs això és el meu paper, detecting
Diu que bé,
natural...
ja està.
Sí? Perfecte.
Sí. Doncs, Núria, jo et diria senzillament...
Perfecte, doncs em quedo aquesta...
Molta estona, però està tot bé.
Vale, gràcies.
Núria?
Hola. Us ha entrat el portàtil aquest que hem endollat aquí a l'HDMI, Núria? No es veu.
Raquel. la butxaca i si faig així, igual es... Hola. Si moc així, si moc el trastet, la motxilla no passa res, no?
Parla una miqueta, sisplau.
Hola. Sí, se sent. Però és que això... Sí. Vale, està bé, no? I si moc la pataca no passa res. Vale, merci. Hi ha una mica de... Sí. Hola, hola, hola. Hola, hola, hola. Per cert, el xerrador que va abans de mi també ho vol. Això. Si voleu provar. Tindràs més fàcil perquè tens butxaca, tu. Do you also want it, Xixian? Els que xerren abans de mi també volen això, si vols provar.
Espera, que baixo. No, aquest ja m'arribava, Sí, espera.
Lucas, pots parlar bé? Pots parlar una miqueta, si ho comprovem?
Hola, què tal?
Vale, tenim bé. Lucas, si vols compartir pantalla, però crec que està bé. Lucas, només una cosa, que ara quan parlis no tinc clar si et senten a la sala. Ara sí parlo. No ho present, vale? Vale, ves la pantalla bé?
Ara mateix no. Ara mateix no el senten.
Vale, ves la pantalla bé. Està tot bé, Lucas? Ja està. Fes una prova, si vols. Bueno, senzillament... Pots deixar aquesta trucada oberta, si vols, i ja està. Senzillament muteja't i deixa compartir pantalla, i pares la teva càmera i ja està. Vale? Sí? Moltes gràcies, Lucas. Després. Adéu. Lucas, una cosa. Sí, segueix la sessió des d'aquí, vale? Perquè amb el YouTube hi ha un retard. No sé si ho estàs llegint per YouTube Live, però l'important és aquesta. Vale? Vinga, gràcies.
Sabia una coseta. No ens quadra el llistat aquest amb les persones...
Aquest es diu Jordi, el canviat, es diu Jordi...
No és Marta, és Jordi, vale. En Jordi vol girar des del 15...
Des de la màquina que és?
Sí, des de...
Un port, és un port.
És Faristol el que farà servir? Sí, Faristol i el 15. Vale. Els dos últims són i la Maia no sé què.
Sí, faran Google Meet. L'he provat jo.
La Maia...
Ho farà amb l'ordinador?
Amb el seu ordinador a través de Google Meet.
Vale, com abans, no? Amb el seu ordinador, que serà, entenc que és PAC 9,
Sí.
No fas un part, no? És el seu ordinador, entra en Google Meet. Amb el seu ordinador personal, entra en Google Meet.
Ah, doncs llavors no, l'ICCV.
és el 8. Vale.
Vale, ja està.
Sí?
Sí, però amb ella podré fer el M4, que amb els altres no.
I tema micros, em sembla que m'ha dit l'Alfred que ara tots volen el micro de demo.
Pues s'haurà de netejar i tot el rotllo,
Si porten mascareta.
Bueno, no sé. al final aquí. Ah, vale, perquè abans l'has enxufat al... Vale. Pues no hauria de sortir aquí.
No, en el GFN2 no enchufaron. Pero en el GFN1 lo he probado y no me ha funcionado.
Però per això s'hauria d'haver penjat aquí, no aquí, no?
No, porque le debe haber puesto la NDI.
Ah, vale.
Si quieres hacer una screen capture, cierra la NDI.
No, ja està, ja la tinc. Aquesta ja la tinc al DDR.
¿Ya estás lanzando la screen capture?
Comencem? Okay, hello everyone and welcome to this second session of the morning. In this session we will have several talks, most of them on natural language processing and multimodal models. So the first talk is given by Xixian Liao, and she's going to present the work, Does Referent Predictability Affect the Choice of Referential Form? A computational approach using mass conference resolution. So, thank you.
Okay, I'm a bit short. Yes, okay, perfect. So yeah, I'm very glad to present this paper. The title of the paper is Does Referent Predictability Affect the Choice of Referential Form? A computational approach using mass coreference resolution. It's probably the longest title. Yes. So, does it work? So this is a joint work with Laura, Gemma, and Matthijs. Okay, so let me first start with our research question. So here we have an incomplete sentence, like Theresa May admired Angela Merkel because. So as an addressee, we hear this context, and then we have expectations about how this context continue, right? So we might think that, oh, wow, it must be because something amazing about Angela Merkel, something great about her, so that Theresa May admired her. So we see that Angela Merkel is very predictable from this context for addressees. And then for a speaker, to continue this context referring to Angela Merkel, they can select from a pronoun she or name Angela Merkel, or even a longer description, a fuller noun phrase, like the first female chancellor of Germany. So we wonder how speakers choose which form to use. Do they use more reduced reference expression, like a pronoun, when references are very predictable from the context? Or in other words, when the context is already very informative about which referent will come next, do speakers use less informative expression, like a pronoun? You know, in this case, they can be more efficient. And previous studies on this question, they got different results. Some of them, they found that predictability affects pronoun production. So more pronouns for more predictable reference. Whereas other studies, they suggested that predictability is unrelated to pronoun production. And as I will explain next, all these studies here, they measure predictability based on predictions collected from human participants. So how did they exactly measure predictability? One type of experiment they used is referent guessing task. So in this type of experiment, participants first need to read a segment from corpus, like I walk to my bathroom and firstly quickly scrub the bathroom tub by turning on the water and racing. So here participants need to predict which is the referent will come next. So they can either choose from reference that have been mentioned in the previous context, or they can write something new. And predictability is measured based on the percentage of participants who can correctly predict the referent. So if predictability affects pronoun production, then we should observe more pronouns in places where most of participants can correctly predict the referent. Okay? But then we found that this approach does not scale well because predictability is measured based on predictions collected from human participants. You have to redo experiments and using different contexts, etc. So this is very costly. Then our idea is to use a computational model to do a similar task and then get estimates for referent predictability from the model. This approach then could be applied in a much more scalable way. Okay? But how can we do that? So first, we found coreference resolution system. So it was the Span-BERT coreference model from Jordi et al. 2020. And it was the state-of-the-art system at that time. And so this Span-BERT system firstly gets an input, like Merkel and Trump were destined to clash, Swiss cool, cultures, and fact-oriented. And then for each mention in the context, this Span-BERT system gives a probability distribution over all the candidate antecedents. So it calculates how likely this mention correfers with each of the mention in the previous context, and also a noun represents a new referent. So you might notice that here is different from experiments with human participants, because here our system, Span-BERT system, can see the reference expression, whereas human participants in the previous experiments, they didn't have access to reference expression. So now to enable the system to predict antecedent based only on the context, but not the reference expression itself, we substituted mentions, each with a mask token, and then train these systems on what we call mask coreference resolution. And this task is inspired on the mask language modeling used in the training of the very famous language model, BERT. Okay? And our model learns to predict antecedent based on only the context, surrounding context, but not the reference expression. So now, after training, for each mention, our new system gives a probability distribution over all the mentions, over all the candidate antecedents. Even it's a mask mention, even without access to the lexical information provided by the reference expression. So now, we basically want to use this model as humans do to predict mentions, but how do we know that the model behavior is sufficiently human-like for this to be a sound approach? So we evaluated our system on the onto nodes test set. So onto nodes is a very large corpus annotated with coreference information and comprises data from very various journals of tests like news articles, magazine articles, Bible, conversation data, and so on. And this table here displays the comparison of performance between the original Span-BERT system and our new variant trained on mask coreference resolution. And as you can see here, when predicting antecedent for unmasked mentions, so it's like traditional coreference resolution task, our new variant retains the same performance of the original Span-BERT system. And meanwhile, for predicting antecedent for masked mentions, our new variant is much better than the original Span-BERT. There's a substantial improvement of 24 points here. And in addition, we also compare predictions from our model to human predictions collected from Jordi et al. 2017. And we found that our system approximates better human expectations than the model constructed by Jordi et al. Okay, so now we believe that the predictions from our model are good enough, and we can use them to test our main question, whether predictability affects mention form. So following previous work, we define predictability in terms of the information theoretic notion, surprisal. So as you can see here, so the higher the probability our system assigned to the correct entity, the lower the surprisal. And a lower surprisal tells us that this referent is very predictable. Okay, so this is how we operationalize surprisal. And now with this surprisal, we study our main question, whether predictability affects mention form. And we first look at surprisal of masked dimensions grouped by mention types. And as you can see here, food and peace, like the first female chancellor of Germany, tends to be more surprising. So it's, in other words, less predictable than pronouns and proper names. So this kind of like a first confirm that predictability affects mention form. And now we wonder, okay, what is this predictability? What is this surprisal? Does our model just learn to predict antecedent based on some shallow contextual cues, like how many times a referent has been mentioned in the previous context, or how far away this referent has been lastly mentioned? So does our model just rely on these shallow cues, or does surprisal actually capture some relevant or higher level information that is more semantically related? So to test this, to test whether surprisal has effects over and above these shallow features for predicting mention type. Following previous work, we did a regression analysis, and it shows that surprisal indeed captured some relevant information that these shallow features have not captured for predicting mention type. So surprisal still affects mention type even when these shallow features are controlled for. Okay, so finally, to sum up, so our results make us more favor the blue camp, which claims that predictability affects pronoun production. And more concretely, our results corroborate previous findings by Tilly and Piantadosi. They found that food and peace are favored and the pronouns names disfavored when we have a higher surprisal. It's just that they got estimates for predictability from human participants, and we got from the model. And also, we extend their finding to larger corpus data. They only look at news articles, but we look at different types of contexts. And from a methodological point of view, we define the mask coreference resolution task. We also show how training a state-of-the-art spam BERT on this task gives us human-like estimates of predictability. And lastly, this approach of using computational model to get estimates allows us to carry out analysis in a much more scalable way in comparison to traditional experiments with human participants. Okay, that's all, I think. Yes, thanks a lot.
Thank you. We have time for one question. Is there any questions? Yeah, actually, I have a question. So,
yes,
what you did is basically based on BERT, right?
Yes, spam BERT is, yeah.
Okay, so could you do, I mean, a similar research based on other transformers, like, I don't know, GPT? Yeah.
Yeah, like, I don't know whether you noticed that, sorry. So previous human participants, they only use the previous context. But here in BERT, we have to take bidirectional context, right? So it's different. So we're also considering using maybe like a auto-regressive model that is more comparable to previous experiments with human experiments. But then in this case, the state-of-the-art coreference resolution system are based on bidirectional models. So there will be, I don't know, there will be more difficulties, but it's a relevant venue kind of for future research. We would like to know. Okay. Yes, thanks a lot.
Thank you.
Thanks.
Any more questions? Okay, let's thank the speaker again.
Thanks.
So now the next talk, it will be by Jordi Armengol. Marta Villegas is a co-author, it's not going to present. Are multilingual models the best choice for moderately under-resourced languages? A comprehensive assessment for Catalan. So thank you, Jordi. The floor is yours.
Hi, thanks for attending this talk. I'm Jordi, and I will be presenting this paper that Marta said, and we're happy to say that it was accepted in the findings of ACL 2021. So first, I will be giving some context on why we did this and why we believe it's relevant. Then we'll see which new datasets we built for the purpose of building better models. We'll go through the experiments, and finally I will discuss the results. So, as you know, this is kind of related to the previous presentation. Mass language models based on transformers are ubiquitous in NLP. They are state-of-the-art in most discriminative tasks, and now with generative models, they are starting to be also state-of-the-art in tasks involving natural language generation. But the thing is that thanks to these models, you can leverage large amounts of unlabeled text, and this is important because text is mostly free. You can obtain text from the internet or books, and this way you don't have to annotate, manually annotate tons of data sets, which is usually very expensive. So originally, these language models were like BERT, were trained for English. Then some researchers developed multilingual models like MBERT or XLM. But then some researchers started realizing that if a language has enough resources, it's usually worth the effort training models from scratch, specifically for these languages. And this was soon discovered in the case of, for instance, French, which has a lot of resources, and German and other languages. But the question here is, literally, you can do that for all languages, but is it worth compared to using a multilingual model? And to give more context from an institutional point of view, the Barcelona Supercomputing Center is leading several publicly funded initiatives from the Spanish government and the Catalan government to improve the state of the art of the NLP for languages in Spain, including Spanish, Catalan, and other languages, and also domains, because, for instance, Spanish is obviously a high resource language, but there is also the biomedical Spanish and the clinical Spanish, or the legal Spanish, and those are not, those have like not so much data. And in this context, there is the DINA project for Catalan and the Maria project for Spanish. Then regarding the pretending corpus, we built a new cleaning pipeline, which is end-to-end. It has several heuristics and different language identifiers, and in general, processing text is not something I would recommend you if you want to have fun, because it's very painful, but it's required, and the reward is usually very high. So the result of this work is the CATEX, which is a new pretending corpus for Catalan, and it has almost 2 billion tokens, which is comparable to, for instance, Finnish or Dutch. And for this, we build also new crawlings, and we use existing ones. Then, unlike other works that have also tried to build language models for other languages apart from English, the thing is that for Catalan, we didn't have a proper evaluation benchmark. So we built the so-called, the CLAP, which is Catalan Language Understanding Benchmark, following the spirit of GLUE in the case of English. And for this dataset, we built new datasets that were manually annotated, and we're quite happy with the results because the quality is quite good, to be honest. And we have many different tasks, like semantic textual similarity, question answering, And this kind of test that usually people assume that they only exist for English, but you can do also that for other languages. So regarding the experiments, the point of the article was more about the resources, not about doing new experiments. But we can see that our bird, the Catalan bird, which we call Berta, is the best performing model. It's better than the multilingual baselines, which are quite strong, to be honest. But a language-specific model has another advantage. That is that it's cheaper to run in inference because the tokenizer is specific to the language. And this means that for each sentence, you have to process less tokens. And since the cost is usually estimated in terms of tokens, this is cheaper. Then we saw that MBERT, which is the Google's multilingual BERT, is a quite strong baseline. And surprisingly, it performs better when fewer examples are available. But as soon as you already had like the 1% of the data set, then the language-specific models we built were better. And also, this is a very obvious and simple thing, but yet it's usually a problem, the tokenization. For instance, if you try to use GPT-3 to summarize a text in Russian, you will see that the text doesn't even fit in GPT's context window. And in this case, our tokenizer, since it's language specific to Catalan, it just segments with less subwords. And this means that, well, it's easier for the model to learn and it's generally cheaper. So what's next? In the same spirit, we have also built a Spanish GPT-2 and a Spanish Roberta. Spanish is not a low resource, but it's also true that before these models, there weren't like many models for this kind of for Spanish. We also built one for biomedical Spanish, and we are trying to build like multilingual models that are also can perform well in different kinds of domains. And also we are very interested in making them accessible to the industry, because we are speaking with banks, for instance, and in their servers they cannot run our biggest GPT-2. So we are interested in making these models easier to run in inference. So that's it. Many thanks. Any questions?
There is a question. I'll let the audience. I'm not sure there is, so maybe you speak up. Oh, yeah, there is.
So you're comparing this multilingual BERT towards the one trained exclusively in Catalan. Do you know what's the percentage of Catalan sentences from the multilingual, if there is any, or is it just trained on a mix of languages which does not contain Catalan?
Catalan is definitely in the MBERT pre-training dataset because they use Wikipedia. So it's a small percentage, but Catalan is there.
So it's in the mix of languages, and then the tokenizer is trained with all of these corpus, with all of these languages.
Sorry, I didn't hear that.
in the mix of languages, and then both the tokenizer and BERT are trained in this corpus of mixed languages, which contains a small fraction of Catalan.
Yeah.
Okay, okay. So I assume that's why mostly underperforms when you have low training examples. Okay. Thank you.
Thanks.
Thank you. More questions?
A veure? Sí. Thanks. That's great resources that you guys are building. So I have two questions. One is like you said that the models are too big to run on some servers, like from banks and stuff. So what are you planning to apply, kind of like distillation techniques to create a better model, and like what's the prospect on that? And the other question is, what are your plans regarding further resources for Catalan? Thanks.
Yes, so we are very interested in, and actually we are working on this area of knowledge distribution, because it's like we don't want to make these models just for writing a paper. We want the industry to use it, and we are receiving lots of complaints, or let's say that are people that, and they are not random people, they are from important banks in Spain, and they cannot execute that in their premises. So this is a problem, and we are working on that, especially with knowledge distribution. And the other, you said another question, or? Mainly speech. So, well, for text, there are many things that are coming, but like basically like generative models and summarization and this kind of stuff. But if I have to say something that it's qualitatively different from what I have said, speech is going to be the next step.
Then I'll go. Congratulations on the nice work, Jordi. I saw very good results on the evaluation, if I'm not wrong. Have you thought about having challenging lifelong learning evaluation data sets? Because at the end, we always keep, learning our evaluation data sets. Have you thought, since you are creating new data sets?
Yes. Yeah, actually we are discussing which will be the new data sets, because now with the AINA project we'll have resources for building new data sets, and long range dependencies is definitely something we are taking into account. For instance, with the Lambada dataset, which is a dataset for English in which there is a paragraph and you have to predict the last word, the word that goes next, but it's not trivial at all, even for humans, to predict which is the, so you cannot use local dependencies for that. So we want to build these kind of things also for Catalan and other languages.
We can thank the speaker once again.
Thank you.
Our next speaker is going to be Gemma Boleda, and she will be presenting the work Object Naming, the Many Names dataset, and what it tells us about languages and computer vision models. Thank you.
Okay, thanks. The work I'm going to present has been done in collaboration with Thomas Brockhagen, Eleonora Gualdoni, Andreas Mettebach, Karina Silberer, Matthijs Westerer, and Zina Tsaris. And we start with the question, can you lower the volume a bit? Podeu baixar una mica el volum o alguna cosa? Estic com... Merci. We start with the question, how do people name objects, right? And let me do a little experiment with you. So if I tell you to please name the object in the red box with the first name that comes to mind when you see it, and then I give you this image, just, you know, I'm assuming that most of you will have thought of duck or the equivalent in your native language. Maybe some of you have thought about bird, and maybe animal, but that's extremely unlikely, all right? So what we did is to repeat this experiment with 25,000 images, and for each image, we gathered names from 36 subjects in English. Yeah. Now, after doing that, for this image that you just saw, 33 people produced duck, and only 3 produced bird. And instead, for this other image here, which also contains a duck, 27 said bird, and 8 said duck. And if you see that the math doesn't add up, because we have 35 names instead of 36, it's because we got errors from humans, so that the data contained a bit of noise, and we cleaned that up after the fact. All right? So now, you can view naming this kind of data, you can view them as categorization, right? Because one of the things we do when we speak is to kind of categorize the world around us. And that is reflected in the lexicon, in the words that people choose. And this is closely related to a task in computer vision, namely object detection, in which the algorithm, the model is asked to detect objects and also categorize them. I don't know if you see it, but in this case, the system, or ideally the system would recognize that this is a bowl, and this is a cup, it said, etc. All right? So this is the task. But in these tasks, typically, you assign one category per object, all right? So you say that this, for instance, is either a laptop or a computer, and you have to make a choice. And this is all okay as long as you stay in a broad categorization system that distinguishes, for instance, between people, vehicles, and, say, grass. But the moment you go to more categories, you are faced with a very, with an issue, which is that many objects, cannot really be categorized only one way. So for instance, let me see if this works. Well, I'll just gesture. In this image here, when we asked our subjects, most of them said woman, but a substantial amount of people said either skateboarder or skater or girl, right? And, they're all right. So this person here is both a woman and a skateboarder. And she can also be described as a girl, which other women cannot really, right? Depending on how their age and other factors. Now, we extracted the many names images from a larger resource called Visual Genome, and one of the types of annotations that Visual Genome provides are labels, standard object detection labels. And in this case, the person who labeled this decided that this person is a skateboarder, right? And this provides a unidimensional view on a phenomenon that in reality is multidimensional, okay? Because we can talk about this person as being a skateboarder or a woman, depending on the communication needs, all right? Now, we think that so this mismatch means that we are not really assessing the capabilities or asking the models to do what they should. And what we do is to kind of assess quantitatively this mismatch between, reality as we see it and what we're asking the models to do. What we did was to compare a state-of-the-art object detection system trained on Visual Genome labels and compare it to the human naming decisions that we have in our data set. And in this evaluation, like this system, because it's a standard labeling system, only returns one name per image, okay? And we evaluated this system in 3 ways. The first one with the labels that come with the visual genome data set, so no many names data here. And in this case, if you remember, this, for this image, it would be counted as correct if the model says skateboarder. The second evaluation is based on the most frequent name, which we call top name, assigned by our subjects. So in this case, because most people chose woman, we are counting like the model's answer as correct if it says woman, and only if it says woman. And the third one is we accept any valid name, any of the names that were provided by the subjects, all right? And here are the results. So in the setup in which we evaluate the model on visual genome labels, the model doesn't really perform very well. We have only 61% accuracy, right? But then when we turn to the most frequent name, there's two things that stand out. The first is that the result suddenly jumps, okay? We have 12% more accuracy, and that's remarkable if you consider that the system has been trained really on this data, right? The system has been trained on visual genome labels, not on our many names data, which is where this gold standard comes from. So what we think that is going on here is that, on average, people will tend to choose a particular name for a given image. As we have seen in the examples, for one image, it will be duck, like 33 people said duck. For the other one, it would be bird, 27 people said bird. And for this one, like the woman example, 17 chose woman. So on average, most of the labels will correspond to the top name in our data. But of course, there's also the other 25% will be quirky labels or less salient labels like skateboarder. So the model picks on the general trends, picks on what it means for something to be a bird as opposed to a duck, for instance. And that explains this jump here. I told you that there's two things that stand out in this result. The first one is this, and the second one is that the model's results are really, really similar to the humans. Why are humans 76% here? Well, because if we evaluate them on how often they choose the top name, only 17 people will be right for the woman case, and the rest will be wrong in this evaluation, okay? And the model is actually really, really close to that. So this is a second remarkable result, and this result extends to the third evaluation, in which recall that we are considering as correct any category assigned by the system that corresponds to one of the names in our naming data. So woman, skateboarder, girl would all be correct. And here we see that again, the performance goes up, and again, we are very, very close to human performance. We have 88 here and 91 here. And so, as we expected, there's this mismatch between how categorization, object detection systems are usually evaluated and how they actually correspond to reality. And I must say that object detection systems, state-of-the-art object detection systems are amazing. They really perform super well compared to humans. And it's remarkable that, depending on how we look at them, we will conclude that they're not performing really well, there's still a long way to go, or they're awesome, right? And we believe actually more the awesome part than the not very well. But these were just questions about, how do we evaluate models and how the models correspond to reality. So I will end by saying that, well, I hope I have convinced you that object naming data, as opposed to the standard classification data, provide, well, linguistic insights, which is something that I haven't talked really in this talk. If you want, you can ask me in the question period. So it's very interesting for us from a linguistic point of view. But also, it provides categorization phenomena that are relevant for both computer vision and also language and vision tasks. And these kind of phenomena that you can uncover with naming data are typically overlooked in standard setups. So I'm hoping that you will find the resource useful. I'm very happy to announce that we just released a stable version, and I hope you will all download it and have fun playing with it. And, and I'll finish here. Thank you.
Okay, questions?
Thanks, Gemma. Yep, here.
Hey, Carlos.
Thanks, Gemma, for this nice presentation. So I have one question that it's about the third evaluation method. I would expect 100% for the human evaluation and not 91. So why we are not having this 100? It's just for the cleaning of the data?
Yeah, that's exactly right. Remember that I told you that there was noise in the data that we cleaned in a second phase. That's why we have many names version 2. In version 1, there were quite a bit of mistakes. And these are things, mainly one thing, which is people naming objects that were not the ones in the bounding box. And that happens, for instance, a lot with clothing items. So you have something that is signaling, for instance, a t-shirt. But then people name the person wearing the t-shirt. Why? Because people are much more salient for humans than clothing items. So there was a clear bias towards people in the data. And in other cases, they provided names that are not really appropriate for the image. And so we cleaned that up in a second round, and that's why we get a ceiling of 91.
Thank you.
Thank you, Gemma. I wanted you to tell us a bit more about the linguistic insights, maybe a TLDR.
Maybe what, sorry?
A short summary.
Yeah, TLDR. Yeah, well, maybe I have some slides on that. Yeah, I do. So the first one is that with this data, we find kind of two conflicting, or like two kinds of evidence. The first one is that we find a lot of agreement in how people behave. Like, well, this is a slightly different estimate, but yeah. So in the clean data, we find that on average, 80% of the people will choose the top name, right? For instance, here, this is even higher, but people will tend to converge on a top name, even though, on a top name. But on the other hand, we also find a lot of variation, right? Because on average, people choose over 2 different names per image. So in this case, they chose, if you put together all the images, sorry, all the names, there will be two names, a bit more than 2 names. So we find kind of evidence for both kind of convergence of behavior, which, I mean, for communication, right, it's nice that we converge on the same names, but we also find substantial variation. So this is the first remarkable result. And the second one, in an analysis that actually my PhD student, Eleonora Gualdoni, who is here, is leading, there's, what we find are typicality effects. So if you remember, when something is very typical for a bird, for a duck, you call it duck. But then if you see it from a different perspective, or on grass instead of water, then you will name it bird. You may revert to bird. And the nice effect that we found is that if something is kind of, there's 2 things. One is more frequent names will tend to kind of float more. So for the strange duck, we got 8 ducks. And instead for the typical duck, we got only 3 birds. So, sorry, I'm not, so basically, there's an effect of how frequent, how lexically available a name is in how we choose it. So for instance, woman is more lexically available, is more frequent than skateboarder, so people will tend to say woman instead of skateboarder, on average. And the other one is that if you have, so the higher the typicality for a category, the higher the agreement in how people name it. But if they are typical for 2 categories, then we will find more variation. So I hope this is a faithful TLDR. Eleonora, correct me if I'm wrong. Okay, she says thumbs up. Thank you for the question, Arianna.
Okay, so we don't have time for more questions, unfortunately, but let's thank the speaker again. Thank Gemma. So, our next talk is, it will be Amaya Salvador, and the title of the talk is Revamping Cross-Modal Recipe Retrieval with Hierarchical Transformers and Self-Supervised Learning. Thank you, Amaya.